Andrew here. In this session, I wanted to cover how we actually run a z-score for two population proportions, and then demonstrate how we can do a power analysis with G-Power. Um, so I gave you the links for both of these in the class. These are both free apps that you can access, or free websites you can access online. In the first one, when you go into the social science statistics link that I gave you, you'll get a page that looks like this, and we're simply going to enter the z-score calculator. The z-score calculator is what I consider to be an epidemiology type test. It compares two different rates. So for example, we have a med-surg unit we've been following for about a year, and I'm just making up the numbers here. I'm considering a 30-bed med-surg unit. I do not know what kind of patient falls in terms of frequencies we have right now. So please bear with me. I'm just simply making up some numbers to show you how this works. But supposing that after a year, we found out that we had 10,000 patient days on our 30-bed unit. I kind of roughly multiplied 30 by about 365. Anyway, let's just say it's about 10,000 to make this kind of simple. But we followed it. We have the data. We had 10,000 patient days. We had 20 patient falls. And we've been studying the literature. The national average should be much lower. Maybe something in the order of about 10 patient falls. So we really have a problem with patient falls. We look into the literature. We look to see what other types of processes have been used to decrease patient falls, and we find something called rounding. And by rounding in this case, there are different ways we use that term, but rounding in this case is that in this method, we're going to make sure that every patient is seen by some staff every 30 minutes. Somebody's going to pass by, look at them. They're sleeping, they're trying to get out of bed, we can maybe intervene. Anyway, we found evidence that this might help reduce patient falls. So we implement that on our med-surg unit. We study this again for another year, and we do much better. This time we only have 9 falls. No, actually I'm going to say something different. Let's go with 10. I'm going to guess here. We're going to go with 10 patient falls for 10,000 days. The days don't have to be exactly the same, by the way, in the z-score calculator. It might be that we only had 9,000 patient days in this separate or second time period. But anyway, and we could be studying two different populations. We could be studying falls at hospital A and falls at hospital B. But anyway, for our example, to make this into what we might use this for in an evidence-based project, is we had 20 falls in 10,000 days. We implemented a new change. We studied it again, and now we have 10 falls in 10,000 patient days. Our significance level, the 0.05, is something you can see that that's our alpha. That's how much risk we're willing to take. If it's 0.05 or higher, if our p-value that we calculate is 0.05 or higher, we will say that we did not find a difference. We cannot reject the null. So that's what that is here. It's already pre-selected for us. You will recall in a prior session I talked about one-tailed and two-tailed tests. A two-tailed test is when we're studying that entire normal distribution. You remember it looked like a bell-shaped curve. There was a tail on the left and a tail on the right. The two-tailed test considers all of the distribution then, whereas the one-tailed test would be used if we only wanted to look at one half of the normal distribution, if we really were definitely sure that we knew which direction our data or which side our data laid in. But the one-tailed test was something that's been used in the past. Every now and then I still see it in the literature that somebody's using a one-tailed test. It's kind of fallen out of vogue. It kind of alters the results and how we look at them. Anyway, we're going to go with the two-tailed test. That's what we typically use now. So all we did was we entered 20 falls out of 10,000 patient days. We wanted to compare that to 10 falls out of 10,000 patient days, and we press calculate Z. So from this, we still have our same data up here. We have our significance level, we have a two-tailed test, and now we have our result. The value of Z is 1.8271, and if you recall, when we have a test, we often use that number that's calculated with our degrees freedom to determine our p-value. But what's really important, the only thing that's important here is that our p-value is 0.06724. By convention, we usually round that off to 3 decimal places, so I would report it as a p-value of 0.067. And because it's 0.05, the result is not significant. So therefore, we can't reject the null. Basically, these numbers are not different enough to claim that what we did made a statistical significant difference, because our p-value is above 0.05, or it's 0.05 or higher, actually, right? So it's interesting to consider this because it brings up another point. I would think that if in a year I could cut the patient falls in half, that would be of great clinical significance. Sure, we'd like that number to be 0. We would hope that we'd have no patient falls or injuries. But if by doing something, and let's just assume that it's something that just was a matter of changing how we work, it didn't add to our cost, maybe we increased patient satisfaction at the same time by being more responsive to patients. But if it's not something that added significantly to our cost, why wouldn't we do it? But this to me is clinically significant. I've cut my falls and injuries in half by doing this process. So clinical, for me, significant. Again, not perfect. Would like it to be at 0, but I've cut my falls in half. Just my opinion, and yours could be different, and that's okay. I would think this is clinically significant, and yet statistically it's not significant. So that is basically how we do the Z-score calculator for 2 population proportions. Again, it's you can access that website online it's free. The other thing I want to show real quickly was the G-Power. If you go to the link that I gave you, you will find information about this test, and you will be able to download it. There are download instructions for a PC. There are download instructions for a Mac. I already have it on my computer. That's why it shows up here like this. It is a free app, and you can do that very simply. Just follow the download instructions. Very easy to use. Once you get to here, I am starting off with this screenshot. I'm in the central and non-central distributions. The first thing I do is I select the kind of test I'm running, and for the sake of our example, I'm doing a t-test. F-test is an ANOVA. These are the X with the little 2 is a chi-squared, and then we have the Z-test that we can run here. But we're doing a t-test this time, so I'll select that. The statistical test within this, there are many different choices here. I'm using, I'm going to run an independent samples t-test, and we've talked about that in a prior session. I have 2 independent means I want to compare, so I'll select that. The type of power analysis, I can choose a priori or post hoc. I'm not concerned about the other ones at this point. A priori, this is something I'm going to do before I start my study. I want to see what kind of sample size I need. Here we go with our tail test again. I do not use the one-tailed test anymore. I find that the two-tailed test is more what we're seeing. The one-tailed test has fallen a little bit out of favor. The effect size is how much difference we expect. After the study, we will actually calculate that. We might know from prior studies, maybe we're repeating a study, we know kind of what to expect. If we don't, we go for the middle point. That's a 0.5, which is a moderate effect size. The error probability, you'll recognize this as our alpha of 0.05. The power is the opposite of that. If you notice, it's subtracted here, but what I want is a power of 0.80. So we're going to switch that. .95 might be something you would use like in a drug study, clinical trial. In engineering, you might see something more like a .99 where there's no room for error. But generally speaking, in healthcare and in most statistical applications, what I see is a power of .80. Remember, at .80, if I get a power of .80, it means I'm 80% certain that what I found in my sample is what's going on in the population. So I can enter that. I entered the test, family, the type of test. This is a priori. I'm doing it before the study. Two-tailed test. Effect size, we're just guessing actually, honestly. We won't know till we run the study, but we're assuming it'll be something in the middle, about 0.5. If you want to be more conservative, you can change this down to 0.3. And when you do that, what you'll do is you'll get a higher sample size as required. Not necessarily a bad thing if it's not too much of a difference. We have our alpha, our power, and then all I do is select calculate. When I do this, when I select calculate, what I get is what's important is the sample size. Here, this indicates that I need a sample size of 128, and typically we would see that as being divided into two equal groups. So one half of the group is getting one treatment, the other half is getting the other. If it's off a little bit, it won't really affect us too much, but we want it as close to this as we can get. And so we need a sample size of 128. And as I mentioned previously, that's what we want to actually finish the study. So we need to kind of have an estimate of how many people will withdraw from the study. It's going to be based on the population we're dealing with. The length of the study might result in more people leaving the study before it finishes. And we will have significant problems if we don't have power. So it doesn't hurt to add a little bit to this. I might go as high as 200. If it's a study where it's going to be something fairly quick, maybe people enter the study and in a matter of a week they finished a survey. I don't expect many people to drop out. I might not need to add too much to this. I might go with a sample size of 150. But a sample size of 200 is not going to really add tremendously to the time and cost of doing the studies that I'm thinking of, so I might go with 200. But anyway, that's the sample size we need to finish this study. Running this test, two-tailed test with our effect size of 0.5 and our alpha of 0.05 and power of 0.8. Let's do something really quick. Let's change this. So we had 128. Let's say we think the difference is going to be very small. The effect size is only going to be a 0.2. We calculate. Notice now our sample size comes up to 788 that we would need. So if our effect size is very low, we'll need a bigger sample size. What if the effect size is pretty high, 0.8? This is the really big difference in our two groups. Our sample size needed is only 52. So again, the 0.5 is a good kind of middle of the road thing to choose. What I found is that if the effect size is really 0.8, we're really going to see a difference. We're really going to come out with results we can use. If the effect size is really low, even getting the 788, we might not have any kind of, we might be able to remember this is about generalizing our results. We might be able to generalize the results, but our p-value might be low anyway. So it might not be worth doing that, even though we can generalize our results that are insignificant. So 0.5 is a good guess if we don't know what our effect size will be. Afterwards, we can do one more quick thing. After the study, we can do a post hoc power analysis. So here, same study, t-test, independent samples t-test. We want to know what kind of power we actually achieved. We calculate our effect size, and it's only say 0.4. We still have our 0.05 alpha. We, we had the 64 in each group that we finished our study with. We go to calculate our power, and our power is only 0.61. So we could have significant results. We could have a low p-value, but with the power of 0.61, we won't be able to generalize our results to the population from which the sample was drawn. But if I'd had about 80 in each group, so you could play around with this and kind of see how the numbers work out. It helps to do that because then you start to understand what's really going on with this. If I had 80 in each group, it's only a power of 0.71. Still not enough. So let's just go ahead and round it up to 100. We thought our effect size might be only 0.4. We do a post hoc analysis, and now we just clear the bar. We have a power of 0.80, so in that case we could generalize our results. So I hope you found this beneficial and interesting. We covered the z-score for two population proportions and how to use g-power to estimate sample size before a study, and then to actually calculate our power after a study.